Okay, let's dive into one of the most fundamental and honestly, one of the absolute strangest truths about our universe. It's an idea that just sounds impossible, but it's the bedrock for everything from the light hitting your screen to the very atoms that make you, well, you.
And get this, that's not some kind of metaphor, that's a hard fact right from the heart of quantum physics. An object can be in one specific spot and also be spread out over an area at the exact same time. So how on earth is that possible? Stick with me because grasping this is going to fundamentally change how you see reality itself.
All right, so to really wrap our heads around this quantum paradox, we first need to get our definition straight, right here in the normal, classical world we live in every day. In our world, the rules seem pretty simple and absolute. I mean, in our day-to-day experience, these two things are total opposites. A particle, like a grain of sand, has a definite spot. It's here. But a wave, like ripples in a pond, is a disturbance that's spread out all over the place. An object just can't be both. Or so we thought. Because when you zoom way, way down to the scale of atoms and electrons, that hard line we take for granted just dissolves. The rules completely change, and suddenly objects aren't forced to choose anymore. They can be both.
Now, this wasn't some easy discovery. For centuries, scientists were locked in this huge debate about the nature of light and matter, uncovering clue after clue that seemed to directly contradict each other. It was a real mystery.
Seriously, this timeline reads like a scientific whodunit. It kicks off in the 1600s. Newton's in one corner saying particles, and Huygens is in the other saying waves. Fast forward to the 1800s, and it looks like the case is closed. Experiments show light interfering with itself, so it has to be a wave. But then, bam, 1905, Einstein comes along and proves light also acts like a particle, which he called a photon. And for the final plot twist, in 1927, they showed that electrons, actual physical matter, could behave like waves. What a mess.
So you can imagine the dilemma for physicists. All the experiments were correct, but they pointed to a conclusion that seemed totally impossible. What is the fundamental nature of reality if everything can be two opposite things at once?
The answer didn't come from proving one side right and the other wrong. It came from a completely new way of thinking, quantum mechanics. Turns out, our experiments weren't wrong. Our everyday intuition was just way too limited. The solution lies in this amazing concept called the wave function.
And this is the crucial part. The wave function isn't a physical ripple in space, like on a pond. It's a wave of pure potential. Think of it as a mathematical map that shows the probability of finding a particle at any given spot. Where the wave is high, there's a good chance of finding it. Where it's low, the chance is, well, low.
So before you look, a particle literally exists as this spread-out cloud of possibilities. But the instant it interacts with anything, a detector, another particle, you name it, that wave of potential instantly collapses, and the particle is forced to pick a spot and appear in a single location. It's a wave when it's traveling and a particle the moment it lands.
Okay, I know what you're probably thinking. If everything has a wave nature, why isn't my desk or a baseball or this table just spreading out like a ripple? Why don't we see this stuff happening all the time? The answer all comes down to momentum. Basically, how much stuff is in motion. Here's the rule. The more momentum an object has, the smaller its wavelength gets. For something tiny like an electron, its momentum is so small that its wavelength is actually big enough for us to measure. But for a massive object like a table, its momentum is huge, which makes its wavelength so ridiculously, unimaginably tiny that it's completely undetectable. The quantum weirdness is still there. It's just hidden from our big, clunky world.
Now this might all seem like some abstract philosophical head-scratcher, but trust me, wave-particle duality isn't just a weird curiosity. It is the fundamental principle that drives a ton of our modern technology.
I mean, just look at this list. Lasers work by treating light as a perfectly organized wave of particles. Solar panels, they need the particle nature of light, those photons, to knock electrons loose and make electricity. The semiconductors in your phone, the MRI scanners in hospitals, and the whole future of quantum computing. None of it would be possible if we didn't understand and control this bizarre, dual nature of reality.
So, we've got to figure it out, right? Everything's both a particle and a wave. Case closed. Well, not quite. Modern physics suggests that this duality we've been talking about is really just two different ways of looking at something even more fundamental.
This is where we get to the modern view from quantum field theory. The deepest layer of reality isn't particles or waves. It's these invisible fields that fill all of space. An electron field, a photon field, one for everything. In this picture, the wave is just the field itself rippling through the universe. And a particle, that's just a concentrated little packet of energy, a vibration in that field. So duality isn't really a paradox at all. It's just two different perspectives of the exact same thing, a vibrating quantum field.
So what this all means is that the universe isn't really made of tiny solid billiard balls. At its core, it's this dynamic, vibrant reality of probability and potential, of fundamental fields that only look solid when we poke them. The world we see every day is just one slice, one manifestation of a much deeper, stranger, and far more connected quantum truth.